Hi, everybody. It's Dr. Kim. So, as I was reading through your final summaries in Unit 10, many of you mentioned predictive analytics, and it's not uncommon. It's one of the things that most students say when they leave this class is that they wish they had learned more about predictive analytics. So, I want to set expectations. And when I respond to you all, I tell you that you have to learn the foundations before you can go to predictive analytics. Um, Tableau is a visualization tool. It was designed to help you explore data, spot patterns, and tell stories. It was not designed to build predictive models. So, what I'm about to show you here lives in Tableau's analytics pane, and it's useful, but it has very serious limitations compared to tools built specifically for predictive analytics. Here's why Tableau falls short and why we didn't cover it in this class. There's limited algorithms. Tableau gives you linear regression for trend lines and exponential smoothing for forecasting, but that's it. Unlike tools like R and Python and SAS that give you hundreds of algorithms, logistic regression, decision trees, random forests, neural networks, gradient boosting support vector machines, and healthcare where you might need to predict patient readmission risk or classify disease severity, linear regression alone is rarely enough. So I understand why you're like thinking, okay, let's get into the predictive part. So we can't validate models here. One of the things that you do when you're working with predictive analytics is you have to split your data into training and testing sets. So you build a model on the training data and evaluate it on the testing data to see if it generalizes. Tableau cannot do this. It fits the line to all your data at once, so you have no way to know if a model would hold up under new data. That's the thing about building a predictive model. You've got to test it. So when you add the new data, you know it's going to perform well. There's no feature engineering or selection. Real predictive modeling involves deciding which variables matter, creating new features, handling missing data, encoding categorical variables, and tuning hyperparameters. Tableau can't do this. You drag a field to a shelf and you get a line. And it also has limited diagnostics. So it shows you R squared and p-values for trend lines, which is a good start, but real model evaluation requires residual plots, confusion matrices, ROC curves, cross-validation scores, and more. You absolutely cannot assess that, whether or not your model's assumptions have been met in Tableau. That's why we don't go into that. And if you literally listen to what I just said, things like ROC curves, cross-validation scores, you just barely were scratching the surface here, learning about pulling data in and finding patterns and visualizing. Predictive analytics is a course all by itself. I teach a machine learning class, and we do all of this. We do clustering. We do build decision trees. We use logistic regression. So lots of things that you cannot do in Tableau, which is why this class does not really get into predictive analytics. So why am I showing you this? Well, there's two reasons. First, the analytic pane gives you a quick visual look at your data's predictive potential. Okay, you can spot relationships. You can see if a forecast makes directional sense, and identify natural groupings, and all without writing code. So predictive analytics is going to require you to write code unless you use a low code or no code platform like SAS, which is used very heavily in healthcare. There's another tool called KNIME, K-N-I-M-E. I teach a class in KNIME specifically. That it's a low code. Some of you mentioned I didn't like the calculations. Well, if you didn't like the calculations, predictive analytics is probably not for you because you have to do a lot of that. So anyway, I just want you to, I want you to realize that the one reason we don't scratch the surface of the predictives here in this class is, first of all, Tableau has limited capability, and second, you really have to learn to code. Again, unless you use a no-code platform, but you gotta wear a heavy statistical hat. Any course I develop that deals with predictive analytics, they have to have a statistics class that's been within the last 5 years. Otherwise, I spend too much time teaching the statistics behind predictive analytics. So anyway, I am going to take that insurance data that I shared with you and do a little predictive so you can play around with it, okay? And so this is where in Tableau you explore and present. Python or R is where you build and validate. So what we're going to do, and you did trend lines. So we've used trend lines. We've added a line to a chart and noted whether things were going up or down, but we never really talked about what the line actually represents mathematically or how to read the statistics Tableau gives you. So that's what I'm going to do. I'm leaving you with this final video to scratch the surface a little bit of predictive analytics as far as Tableau can take it, okay? So we got the insurance data set, and I'm going to name this. This is the one that I used in the webinar 10, okay? So I've got cost versus satisfaction. All righty. So I'm going to drag claim amount to my columns right here. Okay. And then I'm going to drag patient satisfaction to rows right here. Okay. Now, right now, there's only one plot because there's one point right here because Tableau has aggregated everything. All right. So we got to fix this, and we're going to take off the aggregate measures. We're just going to click that. Ta-da! And now look at that. Look at all that. Now we've got about 2,000 individual dots that are scattered across the chart. So each dot represents one insurance claim. The horizontal position tells you the claim cost. Okay. The vertical position tells you how satisfied that patient was. Already without any analytics, you can see that the dots trend downward from left to right. Okay, higher cost claims tend to have lower satisfaction. See, look there. Satisfaction 3.4. The claim amount was 69. Get over here, a little bit higher. Let me get up here. Again, higher scores, patient satisfaction. And I showed you this in the seminar, but anyway, we're going to do more. Okay? So we are going to right-click, and we want to, that's not where I want to do it. So over here, this is what you're normally used to seeing, the data. We're going to click this analytics right here, okay? There's some things here that come up. Again, we've got some box plots and blah, 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 this and that. We're going to choose a trend line, okay? So we're going to drag that over here, and we're going to choose linear, not logarithmic, exponential, so linear, okay? Linear. So as you can see here, when I hover over that, it's giving us statistical information, our R squared and our p-value. So again, you're talking predictive analytics. You're not just talking about things like our patient satisfaction scores show higher to lower, higher the claim is, the lower the patient satisfaction, and vice versa. This is, again, where you have to have that statistical hat. You've got to be able to talk about the statistical output that happens here, okay? And I teach that in my machine learning classes where they are literally interpreting it and turning it in to insights. You wouldn't take this to a chief operating officer at a hospital or the head of this insurance claims company and say, well, the R square is blah, blah, blah. They probably looked at you like you got a third eye. Okay. You got to be able to interpret this for your audience. You've learned during the course of this class that you have to interpret and provide insights and in a way they understand. When you start dealing with statistical information and output, you really have to know what you're doing. So what Tableau did here, it computed the equation that minimizes the distance between the line and every data point. In statistics, this is what's called ordinary least squares regression. Okay, remember, I just said that. So again, that statistic hat had to be on, and it needed to be on really tight, meaning I think somebody said it's been 15 years since they took a statistics class. So if I tried to do predictive analytics with you guys in here, I would spend more time teaching you statistics than actually evaluating models. Okay, so anyway, you don't need to know the math, but you should know that the line represents the best possible straight line summary of the relationship between cost and satisfaction. So here we go. We've got this. I'm going to walk through each one of these. The equation looks like this, okay? Patient satisfaction is equal the slope claim amount plus the intercept. Okay, I'm hoping that y'all sit there and go, what in the world is she talking about? Oh my goodness, now I understand we really didn't get into predictive analytics. Anyway, the slope is telling you by how much. For example, if the slope is negative 0.03003 that we see, that means that for every additional dollar in claim cost, satisfaction drops by 0.003 points. Okay? Seems kind of tiny per dollar, but over $1,000 increase in a claim cost, satisfaction drops by about 3 points on a 0.3 points on a 5-point scale. That is meaningful. Again, predictive analytics discussion. Okay? All right, let's go back to this. And yes, I have notes. That's why you're seeing me click around and click off. Because if I didn't have notes, I'd spend an hour and a half trying to do this. Okay, R squared. R squared is the most important number on this tooltip. You'll see this value here, 0.16003. What R squared is telling us is that the proportion of variation in satisfaction, that is what is explained by the claim cost. Okay? And R squared of 0.16 means claim cost explains about 16% of why patients rate their satisfaction in the way that they do. The other 84% is driven by things that are not in this model, like wait time, staff behavior, facility, the diagnosis, and even the personal expectations. Is 0.16 good or bad in healthcare research? An R squared of 0.16 from a single variable is actually pretty reasonable. Human behavior is complex. There's a lot of things. Think about it yourself when you've filled out a satisfaction survey. There are things that actually drive you to answer the questions the way you do. It could be that I might have given you feedback you didn't like. So if you're asked, would you recommend Dr. Ford to somebody else? I might have made you mad in the class. And whether or not I gave you feedback that was fantastic on some assignments, that one assignment where I used some wording that you didn't like or you thought I could have done better, you're going to probably say, I wouldn't recommend this faculty member, or I might recommend her. I don't know. I'm just saying, human behavior. Human behavior impacts so much, okay? So here's the thing. There's no single factor that's going to explain all of it. And R squared of 0.90 from a one predictor would actually be suspicious. In practice, we add more variables to the model, which we cannot do here in Tableau. That's why we use Python or R or SAS or SPSS. Some of you may have used SPSS before. Anyhow, so let's talk about this p-value that we're seeing right here. It's telling you whether the relationship is statistically significant, meaning that it is unlikely to exist by a random chance alone. With 2,000 data points, you will see a very small p-value, less than 0.0001. Okay? That means we can be confident this negative relationship between cost and satisfaction is real. It's not a fluke of our sample. However, statistical significance does not mean the relationship is strong. A p-value tells you the relationship exists. R squared tells you how strong it is. So you need both. You need both. So as I'm explaining this, I want you to stop and think. Could I have explained that in a report to a stakeholder for the assignments that we did in this class? I hope your answer is no. It's been too long since I've never taken statistics. So again, you gotta have that statistic sitting straight up there in the front of your head. Otherwise, your predictive analytics is not gonna do anything for you. So let's do a little bit more. Okay. I'm going to go back over here to data, and I'm going to drag my diagnosis group to my color. Alrighty. Right. So each diagnosis group now gets its own color and its own trend line. This is where it gets interesting. Look at the slopes. Are they all negative? Yeah, look at that. Are some steeper than others? A steeper slope means cost has a bigger impact on satisfaction for that diagnosis group. Okay? Again, this is not something you would be sharing out with a stakeholder. You would probably create a much different chart than this. And not all charts are meant to be shared with stakeholders. Some of them sit with the analyst, the actual analyst, to start looking at where to go next. Okay. Anyway, all right. Let me get ahead. So if the cancer screening line is relatively flat, it is. Cancer screening that's the blue. Okay. But the mental health line drops steeply. That tells leadership something. Mental health patients are far more sensitive to cost than cancer screening patients. That could inform how you structure copays or patient communication. Also, let's compare our R-squared values across groups. Okay, a higher R-squared means cost is a better predictor for that group. A lower R-squared means that other factors dominate it. Okay, all right, let's just look at some of our R-squares. See, get down here. Okay, again, lots more to interpreting and discussing data that is more statistical in nature rather than visualizing data. Okay. So we could also change our trend lines. Edit trend lines. Notice here, when I first dragged it, there's logarithmic, there's linear. Linear is usually where most people start. Let's try polynomial with a degree of 2. Again, lots of statistics here. Does the curve line fit the data better? Do we think our curve line fits the data better? So notice that Tableau has updated our R-square values. Again, a lot of insight that takes statistical, the ability to translate the statistical output and what it means to our stakeholders. Yeah, again, you can't just go out there and throw p-values at a stakeholder. Anyway, so I am going to stop with this one and let's go to something else, okay? This is forecasting. Forecasting is definitely a predictive method, all right? We're going to name it claims forecast, okay? All right, so we're going to do some regression here. Regression asks this question. What is the relationship between two variables right now? Forecasting asks a different question. Okay? Based on historical patterns, what happens next? That's what y'all are interested in. When you say, I wanted to know more about predictive. Yeah, that's it. You wanted to know, based on what has happened, what's going to happen next. Okay? So Tableau can use something called exponential smoothing, which weights recent data more heavily than older data. Okay? It's not the most sophisticated forecasting method, not at all. Again, that's why we use tools like R, SAS, and Python. But it will work for spotting general direction and seasonality. Okay, so I'm going to drag claim date columns right here. It's year. So what we want to do is we want to drop this down and change it to month. All right, there you go. And it's continuous, which is what we want. You have to have continuous data. I know I've said this to you all before, that when you're building line charts, the data should be continuous, okay? So we want to see monthly data points. So we're going to drag our claim amount to our rows right here. Ta-da-ta-da. All right. So we're going to change this to count. We don't want it to be the sum. We want to change it to count. All right. Now we've got a line chart showing how many claims are filed each month from January 24 all the way over to into 2025, which goes to May or June. Anyhow, so look at the pattern. Monthly volume fluctuates between roughly 98 and 131 claims. There's not a dramatic shift upward or downward. That's already important to know in and of itself. So here's my 98 that I said, and there's my 131. So again, that's our lowest point. That's our highest point. Okay. All right. So we're going to do the forecast. We're going to go back to this analytics tab right here. So this is something we did not do in any of the seminars. So perhaps you find some videos, or even on the Tableau website, because they've got great stuff on Tableau. You learn to use some of these if you want to play around with some of that data that I've given you. So we're going to drag forecast to the chart right here. Forecast, drag it. Okay, drag it here. All right. So we're going to try to project several months into the future. So two things have appeared. We've got a projected line with a shaded band right there. Okay. The shaded band is our confidence interval. Again, that's some statistical talk there. Confidence intervals. It's also called our prediction interval. It represents a range of values that Tableau thinks are plausible. So the wider the band, the less certain the forecast. If the band is narrow, the model is confident. If it fans out dramatically, the model is saying, I'm guessing. Again, you decide based on what you see there. All right. So our data, actually, the forecast is going to be relatively flat with a moderate confidence band. Okay. So this tells leadership that they should expect claims volumes to continue at roughly the current pace, give or take. No big dramatic surge. So the forecast is forecasting about 112. All right. So all right, one of the things, here's something else that's cool. Sorry, I had to pause because I'm hot. Okay, here's one of the cool things. Describe the forecast. We're going to click on that. And here we go. This is Tableau telling you that it used 8 months of data. There's not enough data to search for a seasonal pattern. Okay. We ignored the last month, which is not uncommon. Sometimes in forecasting, you ignore the first 2 months. Really depends on the kind of forecast you're creating. and whether or not you're getting into MAE, MAPE, and other, again, forecast errors. Again, now we're back into the statistical talk again. All right, so this is kind of cool, but it's a limitation because Tableau cannot account for any kind of external events, a policy change, a pandemic, a new competitor who's entered the market. None of those are in the model. So this forecasting assumes the future looks like the past. In healthcare, that assumption breaks regularly because, again. So let's take this off right here. We're going to change the row from count back to sum. Okay. All right. And to look at it again. And of course, it's going to tell you the same dang thing. Or let's take that off. Delete this. Move it. Quit. There we go. Okay. Anyway, so I want to say something like, if we compared the two forecasts side by side, so if the claim count is flat but total dollars are rising, that means that average claim costs are increasing, which is a completely different problem that requires a different response. So if I were, actually, let's do this. Let's change this back. Sorry. Let's change that back to this, and then let's do, you've seen this before, I've done this before with you. Let's go back here. Let's take our claim amount, where we're creating two charts, and this one we're doing sum, and notice the difference in the forecast, okay? All right, so I'd probably show both of these if it had something to tell. All right, clustering. Clustering is huge in predictive analytics. There is a reason why you cluster. You want to find natural groups. My students in my Python and my R classes use k-means clustering and k-nearest neighbors. Again, terms that are very, very predictive and statistical in nature. So we are going to call this claims clusters. Oh. Alrighty, okay? So while regression finds relationships, forecasting predicts the future, clustering answers a different question. Are there natural groups in my data that I did not define myself? Instead of me deciding the category, we let an algorithm decide that, okay? All right, so Tableau uses something called k-means clustering. I mentioned that. It's the simplest clustering algorithm there is. It works by picking a number of groups, which is called K, like the letter K that my name starts with, K, and it assigning every data point to the nearest group center, and then adjusting the centers or centroids until the group stabilize. You do not need to understand the math of this. You need to understand what the output means. So we're going to build a scatter plot for our clustering, okay? So I'm going to drag claim amount to columns. Drag days to the appointment rows. Days to appointment to the rows. I'm such a doofus. I can't even talk. Days to appointment. There we go. All right. And again, we don't see all the dots, so we've got to go up here, and we've got to unaggregate our measures, and voila, got that here, okay? All right, before we cluster, let's look at our scatter plot. You probably see some visual groupings. There are some visual groupings happening here. They're likely a cluster of points at 0 days to appointment, emergency and urgent care visits that didn't have a wait, There are points with moderate wait times, moderate cost. So there may be some high cost, high wait outliers. Outlier. Days to appointment, 45. Get over here. These are all 45. Notice the claim amount. That one's a little bit out there, okay? Again, these, again, remember I said there's going to be some clustered together where there's 0 days, again, because of a certain reason, like they had to go to the emergency room. All right, so we're going to go back to this analytics tab. Again, something we did not do in our class. So look for this, look this up. So I'm going to drag cluster onto my scatter plot right here. Okay. I am going to, it picks the number, Tableau automatically picks the number of clusters. Now, I'm going to tell you, in my Python and R classes, we do tests to help to determine the best number of clusters. We do that by using things like elbow charts or the silhouette method to determine whether or not our cluster, the amount of clusters is actually the best one to use, okay? Okay. Okay, so right here where this shows that we've got our cluster legend right here, you drop this down, you know, when you drop down the little arrows on the pills, that you can do a lot of things, okay? So what we're going to do is we're going to change our clusters, edit our clusters, okay? Let's say 3 right here. Let's try 3. All right. This is the pane. This is why it's kind of cool. So notice now we only have 3 clusters. Orange, blue, and red grouping. Let's try 4. So when I teach this in my R and Python classes, I actually tell my students, or we actually use code to actually to determine which is the best cluster. Trying to do this manually and choosing the number of clusters is just silly. So, but here's the thing. More clusters mean finer distinctions. Fewer clusters mean broader groupings. So, what you can see here too, and notice here, right here, this one also has described the clusters like we did with that forecast on the other. So here's what we've got. All right. So cluster 1, we've got everything listed here. So what cluster 1 is literally low cost, shorter wait. Okay. Actually, it's this one right here, cluster 2. Because I've played around with the clusters. So this does give you that. And then here's models. Here's some models. You click on the model. If you're doing this, this is the statistical part of this clustering algorithm that we're using. So the exact clusters are going to depend on the data, but the point is that the algorithm found these groupings without you telling it anything about provider type or diagnosis. It grouped it based purely on cost and wait time, and the groups correspond to real healthcare delivery patterns, okay? So if I drag my provider, let's go back to our data, provider, to detail, not color, detail, so we don't want to mess up our clusters, all right? So look at the tooltip now. Provider type, look at that. Look at that. Notice that in our clusters right here, emergency department. There's some primary care. There's a few little specialists in here. Most everything up here in our 4th cluster is all about specialists, okay? So anyway, let me change that. And so anyhow, the best, let's just change that back to 3. Okay. All right. So if the algorithmically discovered groups align with real-world categories, that validates both the clustering and your understanding of the data. Again, there's a lot to explain about cluster analysis. That's why predictive analytics takes a full course to teach. Clustering is really exploratory. You're not trying to predict any kind of outcome. You're discovering a structure, okay? In healthcare, this is valuable for patient segmentation, like grouping patients by cost and utilization patterns, so that you can design targeted interventions. High cost, high weight patients might benefit from something like care coordination programs. Low cost, no weight patients might need post-visit follow-ups to prevent return visits. Lots of people have the zero weight. And again, I know during the class, a number of you talked about, and we also explored preventive programs. So this could be an area too. All right, so I'm just going to recap a little bit. So all of these live in this pane right here. Something we did not do. And again, you're not going to get a lot out of Tableau. You're going to get visualizations. And again, this is one of the cool things is the describe feature. So the describe feature here, if we go back over here, this trend line on that, the claim amount, in dollar amounts, again, that's some nice information there, and it gives you your models. And I used those terms a while ago. RMSI. I say RMSI. That may not be the way you say the acronym, but I've always said it as RMSI. So my students in my machine learning classes have to interpret these metrics completely for a stakeholder audience that we should never assume understands the statistical output. Okay, so anyway, this is where Tableau stops and real predictive analytics begins. If you want to predict which patients will be readmitted within 30 days, you need logistic regression, random forests, and cross-validation, something we didn't learn and didn't have time to learn here. If you want to forecast patient volumes, accounting for flu season, holidays, and things like staffing changes, you're going to need ARIMA or Profit. If you want to segment patients across 20 variables instead of 2, again, we just used a couple. You're going to need Python, and you're going to need scikit-learn if you're in Python. I also teach in R, and we use the carrot package, C-A-R-E-T, the carrot package. So what I did today with this video is I'm giving you a taste, a first look, a way to explore whether predictive patterns exist before you invest in building a full model. So that's what Tableau can actually do for you. For a lot of healthcare leadership presentations, a well-placed trend line with a clearly explained R-squared is exactly what that audience needs. Not every insight requires a neural network, okay? So if predictive analytics interests you, I encourage you to explore courses in data science, machine learning, or health informatics that use Python or R. So now you have some vocabulary to take with you. Regression, R-squared, p-value, forecasting, confidence intervals, clustering. So that vocabulary will transfer very well into those advanced tools. Great work this term, everyone. I hope you enjoyed this video. And if you need anything, if I can help you in the future, reach out. Take care.